All right, for lecture 24B, we're going to get into some Mathematica details here to start with. Again, your project should be using Mathematica. So we're, again, looking at the exact same problem here, minimizing the surface area of a cylinder for a fixed volume. Here I've got the functions. I showed you this last week as well. F was the function that is the surface area itself that you're trying to minimize. G is the volume that was equal to a constant. That was the constraint. But they're both functions of h and r, and this is how you enter them in Mathematica. And if, for example, you wanted to do what I did symbolically by hand, solve for h in terms of r, this is the syntax you want to use. This is the constraint equation. There's c. The volume is a constant, is what this means. I'd like to solve this for h. Put a comma h. And this gives me the h in terms of the radius. Remember, h was c over pi times r squared. Right? It's essentially just setting this equal to c and dividing by pi r squared. It gives you this. I can then plug that into the f function, the surface area function, to get this phi function. If you put this into Mathematica, listen very carefully here, however, Mathematica doesn't know that c is a constant. You are thinking of c as a constant. But as far as Mathematica is concerned, if you want the c to be in there, you need to treat it like a variable. I'm putting it as a subscript there with an underscore there when I do the definition, to emphasize to Mathematica to treat it as a variable. I am thinking of this as just a function of r, where c is constant. But I might want to change c to make animations, to animate the graph, for example, as c changes, to see how that min changes as c increases, for example. You can think of that as a function of r, but you've got to program Mathematica to think of it as a function of c as well. And by putting it as an underscore here, it sort of emphasizes I really have what's called a family of functions, one function for each value of c. Conceptually, that's better for me. It also allows me, when I take the derivative of this, to just use a prime instead of that capital D. Question? No? No? Okay. Yeah, then there I do it. Here's the derivative. I could do it with a capital D as well. Put a comma r there to differentiate with respect to r, I should get the same answer. But as far as Mathematica is concerned, I could also differentiate it with respect to c and get something different. I want to think of c as a constant, at least when I'm doing the optimization. Here I'm solving for the critical points. Set the derivative equal to 0 and solve for r. There's 3 of them. Which one do we need? We need the simplest looking one, this one. These other 2 actually happen to be complex numbers, and I don't want to get into that. Cubics can have complex roots. You see like a -1 to a 2/3 power, for example. Well, that's not clear that that's a complex number, but I think Mathematica is thinking of it that way. You can evaluate this this quantity here. This is the height, actually. At this critical value, you find the critical height. By the way, you can approximate these things too. For example, I can approximate this thing. The c is not going to get approximated, of course, but everything else should. The 2 pi to the 1/3 in the bottom there should. There's where I got the 0.54. And when I approximate the other one here, this one here, I think I get 1.08 involved. Double 0.54. Yep, 1.08. That's where I got that back from lecture 8. The optimal height is double the optimal radius. And then I can find the optimal surface area, and I can plug the critical point into the function. This quantity and the other one are going to be in centimeters. This final quantity is going to be in square centimeters. That's the optimal surface area. And I can approximate that as well. This was 5 something times c to the 2/3. 0.54. Here's syntax that will graph this function. For a particular value c, I picked c to be 500 here, 500 cubic centimeters. I know this is very complicated looking code, but this shows the graph and it shows the minimum. And I went ahead and I'm using again c equals 500 cubic centimeters, and now I'm getting actual numbers here. The best radius to use is 4.3 centimeters. The minimum surface area itself is 348.7 square centimeters. You don't see the best height to use out here. You'd have to plug back into the function to find the height. You would plug back into this thing. Well, actually, it was double the optimal radius, right? So the actually optimal height is going to be 8.6 centimeters. Okay. What I want to just show you briefly today, before we go back to the PowerPoint, is even though this code is too hard to understand, we can still work with it and make an animation. This is the main thing I want to get across here. I can put this entire thing inside one of those manipulators that we talked about before. Manipulate around the whole thing. But I can't just stop there. If I enter this as is, nothing's going to happen. Or maybe I'll get the exact same graph as before. Yeah, I get the exact same graph as before. I need an animation parameter. I need something that's going to change via a slider. What should change? How about C? Which, to this point, I'm thinking of as a constant. But now I can say, hey, what if the volume was different? Here's the syntax. Put a comma, then say C goes from, oh, I don't know, 500 to 5,000. But that's not going to make any changes yet either, because I don't have C anywhere else. Where do I want the C? How about the subscript right here? Instead of 500, put a C. How about right here, instead of a 500, put a C? You know what? Actually, I think we're going to get rid of this other stuff, because that's no longer going to be accurate. Let me get rid of this stuff that's in the graphics. This graphics makes the black dot, and it also makes the labeling and the arrow that we see in this picture up here that are red. I'm just going to get rid of this stuff because it's no longer going to be applicable. And the 500 here is going to be a C. Okay, will this work? Let's see. No pun intended. It didn't work. Okay, so sometimes things like that don't work. What do I need to modify here? I think, oh, I got two commas next to each other. I don't want that. Now it's working. And now I can change C, and I see the graph change as C increases. Okay, and it's doing what you would expect. The minimum surface area, as the constant volume increases, occurs at a point up and to the right from the original one. Right? Here's the original one. As C increases, that low point moves up and to the right. In other words, the optimal radius gets bigger, and the minimum surface area gets bigger. That's because the volume's getting bigger. Those have to get bigger. Make sense? The optimal height would also get bigger, we're just not seeing that. As the fixed volume, fixed for any time I stop the animation, increases, the location of the low point moves up and to the right. Optimal radius gets bigger. The minimum surface area is getting bigger. It's because the volume is getting bigger. So those things have to happen. You might wonder, does the cylinder always stay the same shape? Is the height always double the radius? The answer actually is yes, no matter what C is. That's pretty cool. That's an example of an insight you can gain and something you can prove using the more general approach. All right, let's do a couple more optimization problems. This time we'll do them more quickly. And I think we'll just keep doing it by hand for the sake of time. Find the point on the graph of that function which is closest to the origin. This is pure geometry. No real-life application here, seemingly. Though I will say that pure geometric questions often do have real-life applications. It's just not clear what those applications are. We will see some of them later this week. What does this function look like? It's a parabola. It's the standard parabola shifted to the right by 1 unit. y equals x minus 1 quantity squared. I'm wondering, for x between 0 and 1, what point on there is closest to the origin? Find the minimum distance, is what that means. Visually, it looks like it might be right about there. But what point is that exactly? That's what I'd like to find out. And I'm going to tell you right off the bat, it's easiest to minimize the square of the distance, because then you can avoid square roots. You might remember the distance formula by the Pythagorean theorem involves square roots. And it would be nice if we could avoid square roots. The squared distance avoids square roots. And how do you find it? Well, the origin has coordinates 0, 0. What are the coordinates of points along here in general? Well, you don't know where the minimum point is. Let's just label its x-coordinate x. If that point is an x, what are the coordinates of this point? X comma f of x. But f of x is x minus 1 squared. You could initially call it y if you wanted to. Call it xy, but essentially your constraint is that y must equal x minus 1 squared. We've got to be on this curve. The squared distance would be, you take the difference of the first coordinates squared and take the difference of the second coordinates squared. I hope this works out. It's going to be a fourth degree. We may not be able to find it exactly.
Never mind.
I didn't check this ahead of time. We'll see how this works out. I'm avoiding taking a square root here. Is that really okay? Yeah, if you minimize the distance, you're going to minimize the squared distance. If the minimum distance is 0.5 or something, the minimum squared distance is going to be 0.25, 0.5 squared. That's a basic helpful principle. I can avoid taking the square root of this. I'm just doing the squared distance. And I can give this function a name. I can call this f of x, say, and that's the function I'm trying to minimize. I'm a little worried about if it's going to work out because it's going to be fourth degree. So that may not be real easy to do analytically, but let's see how it works out. This is the same as x minus 1 squared. Squared is the same as that squared, because this thing right here is x minus 1 quantity squared. Ugh. I don't know why I started with x to the fourth power there. Let's go ahead and expand that out. So I'm multiplying x squared plus minus 2x plus 1 times itself. Here's the principles. Take the x squared there and multiply it by every term. You get x to the fourth minus 2x cubed plus x squared. Then move on to the second term here, the negative 2x, and multiply it times every term over there. To get minus 2x cubed plus 4x squared minus 2x. And finally take the 1 there and multiply it times everything to get plus x squared minus 2x plus 1. Now combine all your like terms. F of x is going to be a fourth degree. X to the fourth minus 4x cubed. And those two combining. The x squared terms are this one and these three. They combine to give you a plus 7x squared. The x terms are negative 2x in two spots. That's minus 4x plus 1. Okay, I'm not sure that's going to work out. I should have checked this ahead of time. Maybe, I took this out of the book, so I was assuming it was going to work out. Maybe, though, We'll just have to use technology. Maybe that's what they wanted you to do. So x to the fourth minus 4x cubed plus, hopefully I have not made mistakes, 7x squared minus 4x plus 1. Did anybody see any mistakes anywhere? Does it look good to people? Let's see if it works out nice or not. Plug it into Mathematica, solve for the derivative of 0. Is it a nice number or not? Not. Okay, it's approximating it there. I can just do n solve instead, probably. So it's not a nice number. It's going to be irrational. It's approximately looks like 0.410245, where that's the critical value of x, where the point is going to be closest. And then you can approximate the y value by plugging that into the function that I was graphing over there. Take 0.410245 minus 1 squared. 0.3478 is the minimum distance. I could relabel this as x subscript, say. That's about 0.410245. That's the x value where this point is closest. The y coordinate I just found to be about 0.347811. What's the minimum distance itself? Actually, I said that was the minimum distance, but it's not. I've got to plug back into the original function to get the minimum distance. 0.410245. The minimum distance is about 0.29. This distance right here. Okay? 289,273. So it's possible that sometimes you might just have to use the technology to finish your optimization problem. Do you get the main idea? Setting up the picture is important because it helps you see what you're trying to minimize. In this case, find of all the x coordinates along here, which gives you the minimum distance to the origin. In those types of problems, it's best to minimize the squared distance. I'm just telling you that, but it should make intuitive sense so we can avoid square roots. Minimize. Find the derivative of that function, set it equal to 0, solve for x, you might have to use technology. We could check that it's a min with the first or second derivative test. I think I'll just plot it for x between 0 and 1. It is a min. Here's a second geometric problem that I took out of the book. Find the x value, maximizing the shaded area below over the given domain. X goes between 0 and 20, where this blue graph is a quadratic. 1/3 x squared minus 50x plus 1,000. Strange kind of problem. We're not trying to maximize f of x itself. That's the blue graph. We're trying to maximize this red area. Area of a rectangle is base times height. I'm going to give you a problem where it's an area of a triangle instead of an area of a rectangle, but it's a very similar setup. In fact, the blue graph is the same for your problem. You have to use the fact that the area of a triangle is 1/2 base times height. That's a rectangle, it's just base times height. The area of that red rectangle could be thought of as a function of x. The height is the function, this function value, f of x. That's this distance right there. What's the base? Well, that's 0 over there, this is x over here, the base is just x. The area here of this rectangle is x times f of x. That's the function that must be maximized. Let's just try to use that technology to do that fairly quickly. I've got the function plugged in here. Here's a graph of the exact same picture. But what I'm really interested in is I'm really interested in optimizing x times f of x, because that's the area of that rectangle. A of x, oops, forgot my underscore, not good. And then clear A. Got to define functions using underscores, and I do like colons, those two as well. Will A of x have a maximum at some point? Realize it could be at the endpoints in general, though it can't be in this case, because if x were 0, you'd have no rectangle. And if x were 20, it'd be a very small rectangle, it seems. I think it's not going to occur at the endpoints. The maximum looks like it's going to occur around x is between 10 and 11 or something. To find it exactly, solve for when a prime of x equals 0. There's the syntax. There are the answers exactly. And solve will approximate those. We want the one that's between 0 and 20. In fact, if it's past a certain point, the graph, it doesn't even make sense. This is the one between 0 and 20. I said it was between 10 and 11. It's actually a little bit bigger than 11. You can find it exactly. It's evidently this number. Probably the quadratic formula could be used to find that, because a prime of x is going to be quadratic. Something you should be able to do. You should be able to simplify the formula for a of x. It will get cubic, and when you differentiate it, you get a quadratic. Set that derivative equal to 0, solve for x with the quadratic formula. That's going to be the easy thing. But it's this one that's between 0 and 20. Also made an animation using manipulate, showing what's going on here as x changes. You see when x is 0, you really have no rectangle. When x is 20, it's a real thin and long rectangle. It doesn't have as big of an area. The maximum area is when x is around 11.2 or so, right about there. That's the red rectangle that's got the biggest possible area in this constraint. I actually made a double animation here showing both pictures. The picture of the left rectangle on the left and the graph of the function you're maximizing on the right. The maximum area is right about there. That's the a of x function. All right, in our last few minutes here today, I'm going to introduce differential equations. I'm not going to assign any problems related to this for Wednesday, but there will be some problems assigned for Friday. Okay, so this is just an introduction to differential equations. It's not a topic that's always done in Calc 1, but I think it's a really important topic to get in Calc 1 because it helps you in Calc 2 if you take Calc 2. And if you're in physics or chemistry or biology even, differential equations are used. Let k be a fixed constant, and let c be an arbitrary constant. Kind of strange. What does that mean? It means I'm thinking of k as being something specific. I could pretend it's 5. And I'm saying c could be anything. I don't care what c is. That's the distinction. Consider the following family of functions. We have a whole section in chapter 4 about families of functions, so I'm also talking about that section at the same time. Section 4.4. What do I mean by a family of functions? Well, I mean functions where there's a parameter, c in this case, that can be anything. Using a capital C here, I could have used a lowercase c. It's more traditional in this situation to use a capital C, that's why I did. For each value of c, I get one function. But I could pick c to be anything, so I really have an infinite family of functions. Imagine your family had infinitely many people in it. Okay, that's the analogy. For any particular value c, you have one individual from the family. But there's infinitely many functions in the family. In this case, with this particular family, where the function is c times e to the kt, each one of those functions satisfies the following condition. Its derivative is k times itself. Why? Well, just find the derivative with respect to t. Again, my notation is a little funny here. You might say, well, why is there not a comma k here as well? Because there's a dependence on k2. Don't worry about it. It's the distinction between fixed and arbitrary. What's the derivative? C is an arbitrary constant. K is a fixed constant, but it's still a constant nonetheless. T is the variable. Using linearity, the c just goes along for the ride. And then differentiating e to the kt, treating k as constant. I need the chain rule. There's an inside function there, k times t. The derivative of the outside function, plug in the inside function, times the derivative of the inside function, which is just k. In other words, I've got k times the original function. That's phi sub c of t. There's a verification of this fact. What does this mean? It means each of these functions has a derivative which is proportional to itself. That's the key thing I'm trying to get across here. For each one of these functions, no matter what c is, it's proportional to itself with proportionality constant k, actually. The derivative is k times the function. And because of that, we say that each of these functions is a solution of the following differential equation. dy dt equals k times 1. This is an example of a differential equation. It's called a differential equation because it involves a derivative. Differential is sort of synonymous with derivative. Of a function. Y is a function of t. K is a constant. A fixed constant. What are the solutions of these? These are the solutions of this equation are functions whose derivatives are k times themselves. Now you don't explicitly see a y of t here, because it's traditional not to put a y of t in there, because there's actually a good reason for that that we'll talk about more later. But do notice the similarities between these equations. The derivative of this function is k times itself. I'm looking for a function whose derivative is k times itself. These are exponential functions. The solutions of this differential equation are exponential functions. What is that telling us? It's telling us these exponential functions, whether they're growth or decay, grow or decay at a rate proportional to their size. That's a pretty fundamental kind of thing, if it were true in real life. Are there quantities that grow at a rate proportional to their size? And there are many such quantities, for example, populations. At least when populations are small, like people or rabbits or whatever, bacteria in a petri dish, the population tends to grow exponentially. It tends to grow at a rate proportional to the size of the population. No, the more rabbits there are, the more baby rabbits there are. Right? Basic fact of life. That's what this differential equation encapsulates, and that's my intro to the subject. See you on Wednesday.